All right, guys, and let's keep going here in section 2.4. We're now going to get into this concept right here of types of discontinuity. And unfortunately, I just couldn't keep my big fat mouth shut. And we've actually gone ahead and talked about most of these already in some of those examples that we did earlier on in this section. But that said, let's talk about them formally now. So the first type of discontinuity that we are going to discuss is something called point discontinuity. But almost all of you guys know and prefer the word whole when we're talking about point discontinuity. The formal definition of this, everybody, point discontinuity occurs when this happens. When the left-hand limit as x approaches a of f of x is equal to the right-hand limit as x approaches a of f of x. So that right there is enough to say that the two-sided limit does exist, but here's the kicker now, the actual value of f of a is undefined. And this graph over here at the right perfectly illustrates what we're just talking about here. It would appear that as x is approaching a from the left, our curve is going like this, y seems to be approaching a value of b. As x approaches a from the right, y is approaching that exact same value of b. So both the left-hand limit and the right-hand limit exist, and they agree with one another. But the problem with continuity here is that f of a itself is undefined. There is no value here for f of a within this function, or another way of saying that is that a is not in the domain of this particular function. And when this happens, everybody, that graph is what it looks like, and this is what we call point discontinuity or a hole. So an example of this, we've done one of these already, but let's talk about it again. If we were to try to graph this function here, of course you guys would probably notice here that for your domain of this function, x can be every single real number out there except 2. So x is not equal to 2 would be your domain. The easiest way to graph this, of course, would be to factor the numerator and the denominator, and an x minus 2 is going to cancel out and just get you x plus 2. So I'm sorry, this is in fact the same function we've been dealing with a lot. So this function here is going to have a hole right there when x is equal to 2. But other than that hole, it's exactly the same function as y equals x plus 2. So this is what we've got, and again, this would be an example now of point discontinuity or a hole. However, there are certain authors, there are certain textbooks, there are some worksheets out there that like to use this word of removable, I guess I should finish that up, a removable discontinuity for what we're talking about right here. And a removable discontinuity exists when, quite simply, the hole itself can be plugged. So what do I mean by that? If we look at this function that we just came up with right over here, this one right here, f of x, this one has a point discontinuity at x equals 2. But we could remove that by doing the following. We could make a new function, g of x, that is exactly the same, or gives the exact same result of f of x for all values out there other than 2. Or I guess I could have just said, no, actually, let's do that. This is the same as f of x for all x values not equal to 2. But now, to remove the discontinuity, let's go back to this graph over here. And what we would need to do is find a way of plugging that hole right over there. So let's think about how we would write that in our piecewise function. Well, obviously, we need to come up with a plan here for what to do when x is equal to 2. And the y value that we would need this function to take on when x does equal 2 is the same as the value of the left and right hand limits here as x is approaching 2 from either side. And since both the left and right hand limits here are 4, we would go ahead and say let this y value equal 4 when x is equal to 2. Okay, that would be probably the easier way to do it. Actually, I guess the easiest way to do it probably would have been to just do this. If I wanted to remove the discontinuity from that graph and plug the hole, it's basically just the linear function x equals 2. So you really could have done this as well and imply that that works for all real numbers, and that'll actually give you the exact same result as this one right here. It won't always be that easy, everybody, so sometimes you are going to need to go with the piecewise defined function there instead. Okay, so that's a point discontinuity, otherwise known as a hole. The second type here is going to be jump discontinuity. And you may remember that phrase from last year. I think I've shown you one in this section of notes so far that illustrates that, but I haven't pointed it out just yet. Jump discontinuity occurs when your left-hand limit, as x approaches a from the left of a function, is not equal to the right-hand limit at the same a value. So quite simply, when your left and right-hand limits disagree with one another, like maybe it looks something like this, like there's an open dot here, and then either an open or a closed dot here, but this, quite simply, you guys, is what jump discontinuity looks like. The two pieces don't line up. Unlike a point discontinuity, where they do line up, there's just a hole in the middle of the road, if you want to think about it that way. But here, oh man, we messed up bad. The two parts of the road don't even connect. The left-hand limit and the right-hand limit as x approaches a are different from one another. So let's take a look at an example like this. Oh, and that was bad luck on my part. I think I just drew what this one pretty much does. But let's try it. Let's graph the function here, f of x is equal to, and then this whole mess. And you know what? This really wouldn't be a terrible time here to talk about a difficulty that some people have in graphing piecewise defined functions. And I feel like some people make this a little bit more difficult than they need to, so let me run with that. I'm going to completely ignore the bottom half right now and just focus on the top. It's x squared minus 3. I know what that graph looks like. It's a parabola that opens upward with a y-intercept of negative 3. So I'll go down here to negative 3. I'll put my dot right here at 0, negative 3. And now when I go to graph it, I'm now going to pay attention to the domain. This is only true for when x is less than negative 1. So maybe what I should have done a moment ago is just draw the upward opening parabola with a dashed, that was terrible, with a dashed line right, there we go, with a dashed line looking something like this. And now I go back and I solidify that dashed line for x values that are less than negative 1. All right, so let's think about that. If I plug negative 1 into this part of the function, negative 1 squared is 1, 1 minus 3 is negative 2, that's where this graph is actually going to begin, or end, depending on which way you want to look at it. And because this is x is less than negative 1, not less than or equal to, that's going to be an open dot at that ordered pair right there at negative 1, negative 2. So what am I going to do, guys? I'm going to put an open dot right there and graph this solid now for all x values to the left of negative 1. So that is what the left part of this graph is going to look like. And now, really, I can get rid of everything else because none of that applies. None of that is relevant anymore, because everything to the right there happened when x was greater than negative 1. Now, let's go to graph the second part. 3 minus x squared is, of course, a parabola. This one is now opening downward with a y-intercept of positive 3. And I guess maybe we should do this one right. Negative 1 is, again, where this domain begins. So when I put in a negative 1, the negative 1 squared is 1, and 3 minus 1 gets us 2. So this one begins at the ordered pair, negative 1, positive 2. But because of the or equals to right there, this is now going to be a solid dot at negative 1, 2. Now, back to the overall graph of 3 minus x squared. It's got a y-intercept of 3, all right? And I kind of know where this is going already. It's going to connect here like this, and then shoot down like there on the right side. The rest of that parabola would have come down here, but I didn't really need to graph that because all of that was to the left of negative 1, and we only cared about what was happening to the right of negative 1. So I like that. Oh, man. All right, so I like that a little bit better. Okay, so that's our graph, and I guess I'll go ahead and make that a blue dot right there, and that one's going to be closed. Okay, and this is our graph right now for f of x. So what's going on right here? What we can see, everybody, is that this graph right here, f of x, has what we call a jump discontinuity at x equals -1. And the reason for that is the following, everybody. The limit as x approaches -1 from the left of f of x is equal to, well, here's -1, and coming from the left, we are approaching a y value of -2. I could kind of see that right there. But the limit as x approaches -1 from the right of f of x. Okay, so here's -1, and as we approach it from the right, we're riding this little roller coaster. Our y value that we are approaching there is +2. Okay, and again, I could kind of read that from that point right there. And since the left and right hand limits are different, -2 does not equal +2, last I checked, we know then that we have jump discontinuity right here at x equals -1. So this would be the answer, everybody, and this would be the reasoning. So maybe I could have put the word because right over there, but there we go. All right, so we've talked about point discontinuity. We've now talked about jump discontinuity. The third type here is going to be infinite discontinuity. And you might already know just by reading that word what it is that we're dealing with. Another problem that causes a graph to not be one smooth connection from the left to the right is infinite discontinuity. And it is exactly the same thing, you guys, as a vertical asymptote. All right, so an infinite discontinuity occurs at A anytime that your limit as x approaches A, and this is important now, guys, from either the right or the left, when either one of those one-sided limits of your function is equal to either positive or negative infinity, that's when we have a vertical asymptote or an infinite discontinuity at x equals A. All right, so let's see that one in action. And we already talked about this function earlier on, but let's run with it one more time just because it's one that we know well. Y equals 1 over x. Kind of by memorization now, I think we know that we've got horizontal and vertical asymptotes at the x and y axes, and we've got this curve right here and this curve right over here. And what we can see, everybody, is that there is one and only one vertical asymptote in this graph right here. And so we would say that this function right here, f of x, has an infinite discontinuity. Let's be specific now, at x equals 0. And the reason for that would be because, and actually there's two answers to this, because first of all, the limit as x approaches 0 from the left of f of x, let's think about that for a second, guys. As x approaches 0 from the left, we are heading down to negative infinity. Okay, the other reason, one of those would be enough, but the other reason now is the limit as x approaches 0 from the right of f of x. Let's think about that. Now we're over here and we're going up that way. That limit is going to equal positive infinity. Okay, so one of those on its own would be good enough, but we actually have both of them. Now, a couple things that might come up. I showed you a graph that looked like this a while ago. I think it was 1 over x squared, where both parts of this hyperbola were shooting up. Now, your left-hand limit, or I should say the limit as x approaches 0 from the left on that graph, is positive infinity. So is the limit as x approaches 0 to the right. This is still, though, this is still an infinite discontinuity. We still have a vertical asymptote, even though the limit does exist at 0. And if you ever saw one like this is artificial. This is Frankensteinian. This is something you'd have to cook up with a piecewise defined function. But if I just shot over here to one side or another and said, okay, I'm going to make a weird function that does this. Let's say there's actually a dot right here, and the function does that, but then it shoots like that. Okay, and let's just say for the sake of argument, this is a y value of 3, this is an x value of 2. Now in this case right here, guys, the limit as x approaches 2 from the left of whatever this function is, g of x, looks like it's equal to 3. The limit as x approaches 2 from the right of g of x, aha, that one is infinity. So when you look at this, two totally different things happening on the left and the right, this graph that I just drew for you right here still has an infinite discontinuity at x equals 2 because just one infinity here is good enough. You don't need to have it on both sides right there. So we should really read this really as plus or minus, not plus and minus. 1 is good enough to have an infinite discontinuity. Okay, and the last thing we've got right here, this is something I always question, when is the best time to talk about this, and your author decided to put it in here at the end of section 2.4, even though we've kind of already been talking about this idea. The limits of continuous functions. This can get a little bit boring, but here we go. I don't think you guys need to worry that much about decoding and really understanding what this says, because I think it says something you're going to consider obvious. If f of x is continuous at a point now, if it's continuous at x equals a, I'm not saying the function is continuous overall, everywhere, but if it's continuous at x equals a, then, and this is a pretty simple statement, guys, the limit as x approaches a of f of x, that's a two-sided limit, it is equal to f of a, which is the value of the function itself. What this tells us, everybody, is that you can evaluate the limit of a function if it is continuous at x equals a by simply taking that a value and plugging it in for x. That's where the f of a comes from, and that's the phrase plug and chug that we all know and love. But again, pay attention to your hypothesis right here, guys. This method only works if f of x is continuous at a. And I've got to tell you, the majority of the limit problems that we see in chapter 2, the function is not continuous at x equals a. But when it is, this is always the first thing that you should look for and the first thing that you should check before you start to do things that are really difficult and really complicated, because you're kind of missing the joke at that point. So let's take a look at this. The limit as x approaches 5 of the rational function x plus 2 over x minus 3. All right? This particular function right here has a discontinuity. That is going to be an infinite discontinuity, but at x equals 3. That's the one value, 3, that's not in the domain of this function. So I shouldn't have done this in green because I usually do my domain in green. But the domain here would be x is not equal to 3, but that implies that x can equal everything else out there. Well, x certainly then can equal 5. So all we really need to do to evaluate this limit, you guys, is plug a 5 into this expression for x and make it a 5 plus 2 over a 5 minus 3, which last I checked is going to be a 7 over 2, which looks like it's going to be 3.5. There is no need to graph this thing. There is no need to make a table of values on this thing because this function is continuous at our a value of 5. So all we have to do is plug the 5 in for all of the x's. There was one right here and there's one right here, and those became 5s. And then when we do that, we end up with the 7 over 2, which is the 3.5. Now, this would not have worked if we were asked to take the limit as x approaches 3. Because as soon as you try to put a 3 in here, you end up with a 0 in the denominator, and then we would have to do this one with a table or a graph, or maybe some other methods that we're going to talk about later on in this chapter. But since this function is continuous at 5, you go ahead and just plug it in. So moving forward, you guys, when they ask you to evaluate a limit problem, the first thing you should try to do is plug and chug. You'll know right away if something bad happened. If you tried to put in a 3, you would recognize immediately that my denominator became 0, and therefore I've got to use different methods because plug and chug doesn't work. That would mean this function was not continuous at 3, or at a in general. But if you try plug and chug and it does work with no problems the way this one did, then you're in good shape, and that 3.5 is your answer, which you can find lickety split. So that's kind of a nice thing to know moving forward, and it probably should have come sooner in this chapter. But that's a wrap for us right now, guys, on section 2.4. So let's give that homework a try, and let me know if you guys have any questions. Good luck.